All right, so universal gravitation and satellite motion. All right, so let's take a look at. Please calculate the force of gravitational attraction between two asteroids in space where one asteroid has mass of 8.00 times 10 to the 8th kilograms and other one having mass of 6.5 times 10 to the 5th kilograms and are separated by a distance of 13 kilometers when measured from the center of the one asteroid to the center of the other. All right. So this is straight out plug and chug, right? So first thing I would do is I would always write down what's given to us. I know mass 1 is equal to 8.00 times 10 to the 8th kilograms. Right? And mass 2 is given to us as 6.50 times 10 to the 5th kilograms. And the separation, R, is 13 kilometers, or 1.3 times 10 to the 4th meters. You must use meters. Why? Because of this big G. This G has factor of meters in it. All right? 6.67 times 10 to the negative 11th. Right? Newtons times meter square per kilogram square. Therefore, once we know all this, we can actually now use the Newton's gravitation. F is equal to G times m1 times m2 over r squared. So if you plug in all the values, 6.67 times 10 to the negative 11th, right? I'm not going to put the units in this, but you should know these units. And mass 1, 8.00 times 10 to the 8th, and mass 2, 6.50 times 10 to the 5th, right? Divide that by 1.3 times 10 to the 4th, quantity squared. All right, so if you could get your calculator out, and then say 6.67 EE negative 11th, right, times 8 EE 8th times 6.5 EE 5th, right? Whole thing divide by 1.3 EE 4 squared. All right. So you should get, believe it or not, rather a small number. Because if you think about it, this is 13, and then this is negative 11, right? So this will be like second power, but you're dividing this by this, so it's going to be even smaller, right? So I got something like 2.05 times 10 to the negative 4th newtons. That's really small if you think about it, right? That is like 10,000th of a newton. So there's hardly any. That's why it takes like millions of years for these asteroids sometimes to come together to clump up. Okay. Next, a mass of sun is this much. So they gave us the mass of the sun, which is 1.99 times 10 to the 30th kilograms. And the mass of the moon, which is 7.36 times 10 to the 22nd kilograms. The distance from the center of the sun to the center of the moon has an average value of, so R, which is the separation, is 1.49 times 10 to the 11th meters. Calculate the magnitude of gravitational force that the sun exerts on the moon, right? So we know G is equal to 6.67 times 10 to the negative 11th, right? Newtons times meters squared per kilogram squared. So again, if we were to just plug and chug, right? We get 6.67 times 10 to the negative 11th. And then mass of the sun, which is 1.99 times 10 to the 30th. And mass of the moon, 7.36 times 10 to the 22nd. Whole thing divided by, right, 1.49 times 10 to the 11th squared. All right, so let's check it out. So 6.67 EE negative 11th times 0.99 EE 30th times 7.36 EE 22nd. Whole thing divided by, right, 1.49 EE 11th, right, squared. All right, so what do we get? I get something like 4.40 times 10 to the 20th. Okay, 10 to the 20th newtons. So the answer is correct. All right. Next, small steel spherical object located on Earth's surface at a distance of this much. This is actually the radius of the Earth, by the way. Right? From the center of the Earth, experiences a gravitational acceleration of this much. Use this information, right, and the law of universal gravitation, where G is this, to calculate the mass of the Earth. Well, we already know the mass of the Earth, but let's try to see if we could calculate that. So we know mass, right, of a sphere, right, which we really don't know. Right? We also don't know the mass of the Earth. That's what we're trying to find out. We also know the distance of the separation between the sphere and the Earth happens to be the radius of the Earth, which is 6.38 times 10 to the 6 meters. We also know acceleration due to gravity G is equal to 9.799 meters per second squared. And we also know that big G is 6.67 times 10 to the negative 11th newtons times meters squared per kilogram squared. Now, they're asking us calculate the mass of the Earth. Well, how do we do that? It's really not that hard because we know on the surface of the Earth, the gravitational pull, right, can be calculated as Fg. That Fg is equal to mg. But that also is same for this F big G, which is G times m times the big M, mass of the Earth, right? Divide that by r squared. So these two are same actually on surface of the Earth. These two are also same because they're same gravitational force. So we can set them equal to each other, saying the mass of the sphere times G is equal to G times the mass of the Earth times the mass of the sphere divided by r squared. Notice what happens to the mass of the sphere. It gets canceled out. It doesn't matter which mass we use. We could use mass of U even. Right? So now we know a lot of things here. And let's solve for mass of the Earth. So if we bring this to the other side, we get G times R squared, and then divide both sides by big G, and we get left with mass of the Earth. Therefore, G, which is 9.799, times R, which is 6.38 times 10 to the 6, you have to square that, divide that by, right, 6.67 times 10 to the negative 11th. So let's calculate the mass of the Earth. All right, so here, 9.799, right, times 6.38 E6 squared, right, divide that by 6.67 negative 11th, right? And then, when we do that, we get, look at this, we get 5.98 times 10 to the 24th kilograms. And that is pretty much the accepted value for the mass of the Earth. When Lord Cavendish was working on this universal constant G, people were asking him questions like, "So what are you doing? I mean, like, what project are you working on?" And he basically said, "I'm trying to weigh the Earth." and he basically was trying to calculate this by figuring this out, and he did that actually, and he did it very well, and he weighed the Earth, you know. All right, next, let's take a look at universal gravitation again. Now this time Hades has mass 2 times that of Earth and has radius 2 times the radius of the Earth, right? What is acceleration due to gravity G on that planet Hades? Well, we know mass of anything on the planet times G of Hades is equal to, right? We know it has to equal to G times, right, mass of that anything times the mass of Hades over the radial distance from center of the Hades to the surface, which is radius of the Hades squared. So we're trying to find what this G is, right, relative to Earth. Well, we know these two masses can cancel out. Then G, acceleration due to gravity of Hades, is equal to G times. Now here, the mass of Hades is equal to 2 times that of Earth, 2 times the mass of the Earth. Right? 2 times the mass of the Earth. Divide that by the radius of Hades is 2 times the radius of the Earth. So 2 times the radius of the Earth, quantity squared. Now, if you take a look at this and work it out, so here I got G times the mass of the Earth times 2 over, here when I square this inside the parentheses, it becomes 4 radius of the Earth squared, because it's 2 squared RE squared. So what does that become? This becomes 1/2 of G times the mass of the Earth over R Earth squared. We already know what this is. This right here is 9.8 meters per second squared. Because this is acceleration due to gravity on Earth. Right here. Therefore, acceleration due to gravity on Hades is equal to 4.9 meters per second squared. You don't even have to figure all these out by putting in all these numbers, because we already know that this has to be 9.8 meters per second squared. All right. All right. Good. Next. All right. Now we get to satellite motion here. So I have 2,000 kilogram satellite. It's moving in a stable circular orbit at an altitude of this many kilometers above the Earth, right? So I think it's a good idea that we change this into meters, right? What the heck is that? I guess this is in the wrong place, huh? This comma is in the wrong place. So if you think about it, kilometers is 10 to the third, right? 6, 7. So it's like 1.914 times 10 to the 7th meters is what this altitude is. Now remember, r, the orbital radius, is equal to altitude plus the radius of the Earth. So that you have to understand that, right? Because if you were to look at the Earth and the satellite, this is r right here. From here to here is r, right? And that is the radius of the Earth plus the altitude, right? So r is equal to altitude plus the radius of the Earth. Therefore, if we were to look at this, my r then is equal to 1.914 times 10 to the 7th plus 6.38 times 10 to the 6th. So what's my r? Okay. So my r is 1.914 EE 7th plus 6.38 EE 6th. I get 2.552 times 10 to the 7th meters as my orbiting radius. That's good to know. We need to know that. All right, so please calculate the orbiting velocity of the satellite. Now you could just look that formula up, right? But let's see if we can actually rederive it. So we know the sum of all forces is equal to, in circular motion, is equal to MAC, right? And in sum of all forces in circular motion, there's only one force that's causing this to go in a circular motion, and that is F big G. And since F big G is in the same direction as my AC, then they're both positives. So MAC is equal to F big G. Therefore, mv squared over r is equal to, now this mass here, of course, is the satellite, because that's the one that's going around the Earth, is equal to g times the central mass, which is mass of the Earth, times the mass of the satellite, divided by r squared. So again, we can cancel out the mass of the satellites and cancel out one of these r squares with r, giving me my orbiting velocity is equal to square root of g times the mass of the Earth divided by r. Okay, so we derived it again. So here we can use that now. V is equal to square root of, right, 6.67 times 10 to the negative 11th times the mass of the Earth, 5.97 times 10 to the 24th. Right? Whole thing divided by r, which we calculated earlier, which is 2.552 times 10 to the 7th. So what's my orbital velocity? Right. Well, let's get this done. So here, we have 6.67 EE negative 11th times 5.97 EE 24th. Right? Divide that by the radius of the Earth. Right? So I get this. This is a checkpoint here. So square root of 15603,409.09. Okay, that's the checkpoint. Now I should take a square root of that, John. So my V orb, my orbiting velocity should come out to 3,950.1 meters per second. All right, so what is the period of that, right, in hours? So here we have period, so V is equal to 2 pi r over the period. So the period, T, is equal to 2 pi r over V, which is equal to 2 pi times 2.552 times 10 to the 7th. Divide that by 3,950.115, right? So what is that? So 2 times pi times, right, 2.552 7th, right? And then divide that by 39.50. And I get something like 40,592.97 seconds. But they wanted that in hours. So my period is equal to, so divide that by 3,600. Right? So if you do this, say 1 hour is equal to 3,600 seconds. The seconds will cancel out, giving me 11 hours, 11.3 hours. Wait, this sounds familiar. Looks like we already did this problem before. Geosynchronous satellite we already did. It should be in your notes. Okay, this should be in your notes. We already did the altitude and the orbiting velocity of the geosynchronous satellite, and I'm not going to redo that. So hopefully that was a good practice for you, and then we can actually move on. Okay. Any questions? All right then. Let's take a few minute break, I guess. If you want to, you can take a look at the geosynchronous satellite one. I'll put this up here so you guys can actually take a look at it. Okay, the geosynchronous satellite one is here. So, if you have no questions, then what I'm going to do is I'm going to give you guys a little break before I send you to do your assessment. Now, for those of you who worked out the extra credit, I will place. I was thinking of just spot checking it, but I think that's going to take too much time, and that's a waste of time. So I placed someplace on Schoology for you to post. Now, if you actually have the correct answer, you can post it up there. And if you had anything close to 1,800 revolutions per day, you can post it up. Okay, and I will give you extra credit on that. All right. All right, then I'll stop my lecture here.